Okay, so circular motion, Chapter 5. Chapter 5 covers both circular motion and gravitation. In this lecture, I'd like to cover the first few sections of Chapter 5 on circular motion. So, first of all, let me define uniform circular motion is motion in a circle of constant radius at a constant speed. Instantaneous velocity in this case is always going to be tangent to the circle. Okay, so if you look at which direction the particle is traveling at any given instant in time, it'll always be pointing tangent to the circle, as is shown in this figure. But because the velocity is always changing direction, then that means that we have an acceleration. If you draw a little triangle of the velocity v1 and v2 at some time where they're separated by not much time, then you can do some vector subtraction. And you can see that the delta v, which is going to be in the same direction as your acceleration, is going to point in towards the center of the circle. So the direction for the acceleration for a particle moving at constant velocity in a circle of constant radius, the direction of the acceleration is going to be pointed in towards the center of the circle. The magnitude of the acceleration is the speed squared divided by the radius of the circle. This acceleration is called the centripetal acceleration and sometimes called the radial acceleration. Okay? Now, just like the velocity is constantly changing direction, so is the acceleration. Okay? It's constantly pointing in towards the center of the circle, and that changes as the particle moves around in its path. So for an object to be moving in uniform circular motion, because it's accelerating, that means that there has to be a force on it, because F is equal to the mass times the acceleration. Okay? We already know what this acceleration is. It's our radial or centripetal acceleration, which is equal to v squared over r. And so we know what the magnitude of the force is, the centripetal force, which is mv squared over r. Now, the centripetal force is supplied by different forces that we already know about. For example, if you whirl a ball in a circle and the ball is being held by a string, then it's the tension in the string that supplies this centripetal force. If it's a car going around a curve on a highway, then it's the frictional force between the tires and the road that supplies the centripetal force if the road is flat. If it's the moon going around the Earth, then it's the force of gravity that's supplying the centripetal force there. You might have heard of centrifugal force. Okay, this is a fictitious force, a false force. There's no force that points outward. What you're feeling there when you go around a curve in your car and you feel kind of slung towards the outside of the curve, what you're feeling there is your tendency, your desire to continue going in a straight line. Okay, and then it's the friction between your butt and the car seat, or the force of the seat belt on you that keeps you in your seat. Okay. If that were to vanish, if those forces were to vanish, then the object that was moving in the circle would fly off tangent to the circle. Now, here's a couple of points to think about when you work problems. A lot of students get confused because they think that the centripetal force is just a force in and of itself, like gravity or tension or friction, but it's not. The centripetal force is supplied by something else, one of these forces that we've already learned about. What this means is that when you do your sum of the forces equations, like you did in your previous chapter, you're going to have problems a lot like that for this chapter. When you do your sum of the forces equations, then that means that the sum of the forces is going to be equal to mv squared over r. But the sum of the forces acting on the object in the radial direction might be, for example, the normal force minus gravity or something. Anyway, the sum of those forces equals mv squared over r. mv squared over r is the result. Okay? It's also easiest for these types of problems to think of the radial direction rather than x or y. And then what we're going to do in the problems, example problems that I work for you, is take pointing in towards the center of the circle as the positive radial direction. Okay, so that's just the choice that I'm going to make, and I'll point that out as I do the example problems. So first of all, here's the first example problem. You might have ridden this ride at a fair or something. Lots of times they call it the gravitron, but sometimes it has other names. Okay, so here you go. A 60-kilogram person is riding a gravitron. The coefficient of static friction between the rider and the walls equals 0.15. The radius of the gravitron is equal to 12 meters. What is the minimum tangential speed required by the gravitron in order to prevent the 60-kilogram rider from slipping to the bottom of the gravitron? So if you haven't ridden this ride, let's assume that you're riding the one that only goes in a horizontal circle. Although there's one at Tweetsie that goes in a horizontal circle and then tilts up too, and the physics there is slightly different. But let's say you're riding this ride, it spins you in a circle, and then what usually happens is once you get up to speed, the floor will drop from out under your feet, and you'll be pinned to the wall just by the acceleration, the turning of the gravitron. Okay, so let's work this problem. In this case, the force of friction is acting upwards on you. Okay, that might seem a little weird, but remember you're pinned to the wall and gravity is trying to pull you down. And so friction is always going to oppose the direction of motion, and so that acts up to oppose gravity. And then we're going to take our radial direction as the horizontal direction, right, because the circle is in a horizontal plane. Okay. And the normal force is the force that's pushing you, the wall is pushing on you, okay? So that's the force of the wall pushing on you in the positive radial direction, okay? So in this case, it's the normal force between you and the wall that is keeping you in that circular path, okay? So let's do the sum of the forces in y first, okay? Now the y direction in this case is up and down and not in the plane of the circle. So the sum of the forces in y is 0 because you're not accelerating in the y direction. You're pinned to the wall, okay? And that's equal to the force of static friction between you and the wall minus gravity mg acting downward. Now, we know that our force for static friction is equal to the coefficient of friction, mu sub s, times my normal force, okay? And then I subtract off minus mg for gravity. So that's one of my sum of the forces equations. Now the other is for the radial direction, which here is x, okay? So the sum of the forces in the radial direction is always going to be equal to, for these problems, mv squared over r, okay, which is your centripetal force. That's the resultant force, and in this case, the forces that are acting in the radial direction, the only one we've got is the normal force, and the normal force points in towards the center of the circle, so it's plus n, okay? So now we're going to take our top equation for the sum of the forces in y and plug in and solve for our normal force, okay? Oh, I'm sorry, we're taking our sum of the forces in the radial direction and we're going to solve for our normal force. And so here the normal force is equal to mv squared over r, okay? And then we plug in for that in our top equation. Okay, so the top equation says the sum of the forces in y is equal to 0 is equal to mu sub s times my normal force. I'm going to plug in for my normal force, mv squared over r, right, and then subtract off minus mg. So now I have an expression, and I can solve for my speed, which is what I really want. And my speed, I'm going to take this mg over to the other side of the equation. The mass appears in all my terms, so I can cancel it out. So to get my speed, right, then I have mu sub s v squared over r is equal to g. I multiply through by r, divide out by mu sub s, and take my square root. So I get the speed is equal to the square root of rg over mu s, and I plug in for the numbers that I have from my problem, and then I solve for my speed, which is 28 meters per second. So that's how fast it has to be going for the person to not slip down the wall. Now, if you go back and look at the problem, it really emphasized that this was a 60-kilogram person, but that was a bit of a red herring because it doesn't matter how much the mass the person has. The mass cancels out on both sides of the equation. So whatever speed will work for the little 5-year-old kid will also work for the 50-year-old guy with a beer gut. All right. Now let's move on from horizontal circles into vertical circles. Okay? Vertical circles are a little different because you'll have a different sum of the forces at the top versus the bottom of the loop because of gravity. Okay? Let's say, for example, that you're a fighter pilot and you're traveling in a vertical circle here, all right? So at the bottom of the loop, the fighter pilot is oriented upward, okay? And the seat will exert a normal force on his butt, keeping him in the plane, and the normal force is in the upward direction, okay? And gravity is in the downward direction, all right? Now, those are the forces that are pointing in the radial direction. So the sum of the forces in the radial direction, which is equal to your mv squared over r, your centripetal force, okay, that's going to equal to the normal force minus mg, because the normal force points in the positive radial direction towards the center of the circle, but in this case gravity points away from the center of the circle, so it gets a negative sign. So you have n minus mg equals mv squared over r. And if you solve for your normal force, then you'll get mv squared over r plus mg for your normal force. And that makes sense. I mean, if you think about it, when you've been going in a vertical circle, say on a Ferris wheel, for example, okay, and you're at the bottom of that loop, you feel heavier in your seat than when you're at the top of the loop, okay, where you feel a lot lighter in your seat. And that's what the normal force is telling us. Now at the top of the circle, okay, the plane gets inverted in this case. So the plane is inverted in this case. So now the normal force and gravity are going to be pointing towards the center of the circle, right? My normal force points down, and so does gravity. And the direction to the center of the circle is down. So this is all positive because the radial direction is positive when it points towards the center of the circle. So here I have normal force plus mg equals mv squared over r, okay? And that means that if I were to solve for my normal force, I would get mv squared over r minus mg, all right? Now be careful here. In these problems, if you are looking at where it will fall out of the center of the circle or where the pilot will fall out of his seat, okay, that would be when the normal force goes to 0, because the normal force is the force with which the seat pushes back on the pilot. If that goes to 0, then the pilot's not being held in the seat anymore. He's not touching the seat. Okay, so if mg equals mv squared over r in this case, then that would mv squared over r minus mg would go to 0, and the normal force would be 0. And that's why you really have to crank your speed up, right, to stay in your seat at the top of that circle. You have to be going faster. I'll do a demo in class spinning pails of water and things like this around. And so what I have to do when I do these demos is to get the pail of water going fast enough so that the water doesn't fall out. So here's an example problem based on that. A pail of water is rotated in a vertical circle and the radius is 1 meter. What's the minimum speed so that the water doesn't spill out of the pail at the top of the circle? Okay, now in this case, down is going to be positive because it points towards the center of the circle, and that's the positive radial direction. Okay, so it's pointing towards the center of the circle and the pail is at the top. I've done my free body diagram over here, and you can see that normal force and mg are both down, and that's also the radial direction. So the sum of the forces in the radial direction is equal to mv squared over r, which is equal to the normal force plus mg. And I say, when a normal force goes to 0, that means stuff is starting to fall out of the bucket. Okay? So to find the minimum speed so that water doesn't spill out, then let me go ahead and set that normal force to 0 to find that minimum. And then I'll know that I have to spin the pail faster than that. So in that case, mv squared over r would be equal to mg because n goes to 0. And now I can solve for my speed, right? I would cancel out my mass, which appears in both terms, multiply through by my radius, and take a square root. So the speed was equal to the root of g times r, which in this case gives me a speed of 3.1 meters per second for how fast I have to spin that pail in order to keep the water in. Okay, let me continue on now with highway curves that are banked and unbanked. So if you've got a car and it's going around a curve, there has to be that net force towards the center of the circle. Otherwise, the car will just skid out and not be able to follow the road. If the road's flat, then that has to be friction. Okay? If your frictional force isn't big enough, then the car will tend to move in a straight line and get skid marks, like are shown here in this picture at a racetrack. Okay? So as long as the tires don't slip, the friction is static friction. And that's because as the tire rolls through, each point on the tire is still with respect to the ground. If you start to skid, though, then a particular point on the tire will be dragged across the surface, and that's kinetic friction. And that can be bad for a couple of reasons. First of all, we know that our kinetic coefficients of friction are generally smaller than our static coefficients of friction. And so that means that there can't be as much kinetic frictional force supplied as static. Okay? Also, the static frictional force can point towards the center of the circle, but the kinetic frictional force opposes the direction of motion. Okay? And that means that it's going to be more difficult to regain control of the car and continue around the curve in that case. So lots of times you'll bank the car, or bank the curve, so that the cars don't skid. And you'll see this in a lot of exit and entrance ramps to freeways. Banking the curve can help cars from skidding, and for every banked curve you can actually solve, and engineers do this when they build roads, you can solve for the speed where the entire centripetal force is supplied by the horizontal component of the normal force, and then friction's not required. Okay? So here I show a car going around a bank, okay? And the bank has an angle theta with respect to the horizontal. If you ignore friction and you just draw the free body diagram, then you've got gravity acting down and the normal force acting perpendicular to the bank. Okay, so this normal force is going to have two components in the x and the y direction. Okay? Now remember, for these types of problems, what we're interested in is the radial direction. And here the radial direction is going to be in the horizontal direction for the curve. Okay? So I want to break it into the x and the y. All right? So if I do that, then the radial direction here, which in this case is the x, okay, that's going to be the normal force times the sine of theta if you use your trig. Your angle theta is here with the y-axis, okay? And remember that the sine of theta is the opposite over the hypotenuse, all right? So you use sine and not cosine. So the normal force times the sine of theta is equal to mv squared over r, okay? And that will be your radial force. All right, so let's do a banked curve problem so you can see a little better what I'm talking about. An engineer designs a banked curve so that cars won't have to rely on friction to keep from skidding. Suppose the speed limit on the curve is 30 miles per hour, okay? And if you do the conversion, that translates to 13.4 meters per second. And let's also assume that the radius of the curve is 50 meters. So at what angle should your curve be banked? Okay, so here's your free body diagram. It's the same as the one on the previous page. Your radial acceleration or your radial force will be in towards the center of the circle, okay? And you've got your normal force and mg acting downward. So let's do the sum of the forces. The sum of the forces in y is equal to 0 as long as the car doesn't go up or down the bank. Okay, so we're going to assume that's the case, set that y direction equal to 0, and then you have the normal force times the cosine of theta minus mg for gravity as your forces in the y. Gravity points down, and remember you're only taking part of that normal force. Okay, the sum of the forces in the radial direction, that's going to be equal to mv squared over r. And the only supplier in the radial direction is the normal force component, f sub n sine of theta. Now we're going to use our y equation here and solve for f sub n. So since f sub n cos theta minus mg is equal to 0, then f sub n cos theta equals mg, and then f sub n is equal to mg divided by the cosine of theta. If I plug that expression in for my normal force in my radial force direction, okay, then I have mv squared over r is equal to mg over the cosine of theta times sine of theta. Now, the definition of the tangent of theta is the sine divided by the cosine of theta. And so that's mg tangent of theta. Now, I can solve for theta here. So tangent of theta is going to equal to v squared over rg because that mass cancels out because it's on both sides of the equation. So if I solve for tangent of theta, v squared over rg, in this case, plugging in the numbers that I have for this problem, I get a tangent of theta is 0.3664. And so if I take the inverse tangent to find the angle, I get 20.1 degrees. Okay? So they bank that curve at 20.1 degrees, and then they don't need friction. Now here's some points for bank curves. The banking angle, as you saw in the previous problem, is independent of the mass of the vehicle. If the car rounds this curve at a speed less than the design speed, the friction is necessary to keep it from sliding down the bank. Okay, so gravity will start to overcome and it might slide down the bank. If the car rounds the curve at more than the design speed, then friction is necessary to keep it from sliding up the bank. Okay, so those are the two cases. And you can see here in the drawing that the angle has to increase as the speed increases. And if you've ever been to a racetrack, you'll know that some of those banking angles are really big for those tight turns. And this one shown in the picture is 31 degrees, which is pretty impressive. Okay, I'll see you in class.